that's not like.
Maybe
That's
Okay.
not as important.
There's a homework you'll see.
There's a homework I'll see.
Yeah.
Okay.
So okay, I'm gonna get going. How's everybody doing today? Got some. Not sick. All right. Got some thumbs up. There's a homework due Friday. I didn't actually look at it till today, so if you didn't do it over the weekend, that's all right. But a lot of you did it, but some of you missed it. So please do the numerical assignments. I'm going to go over it now. Actually, let's talk about what we're doing today. Where's my thing? Okay, so today we're going to go over the the fifth numerical assignment. And there's a paper homework that will be due Friday. It's not there yet. It'll be there by the end of the day. Office hours are 2:30 on Thursday. So Thursday at 2:30, come to office hours. This homework set is not easy. So make sure you start it early, get all your questions sorted out, and then come to office hours and we can do the homework together. So numerical 4. Let's do numerical. Notebook. So this numerical homework is really straightforward if you read it carefully, because I give you all of the answers in the text. I spell it all out for you. So if you read the thing carefully, there's no reason for you to not get the picture that I got at the end and to get the right answers. It's all really spelled out. However, there's a big startup bump of what the hell is he talking about in the first place, because it's not necessarily the easiest material to digest. So let us go through and talk about what's in it. So okay, we start off with the same block of stuff. We have a black body function, which I defined for you this time. I had made you write it before. Now I just gave it to you because I don't need you to reinvent the wheel every time. And an array of wavelengths that we'll use. And then there's this constant that comes from the normalization. This is the magnitude of an A star minus the flux of an A star. Okay, so it goes through this long, kind of drawn out blah about color. So let's talk about that for a second. Let's also give us some more light. Which of these boards is more easy for you guys to see? Is that one? All right. Was that? Yeah, but I think the people in this corner probably can still see this one. You guys probably want that one better, but I think on average, you guys cannot see that board, so we'll go with this one. That's not a bad attitude. Okay, so I just need to talk about color for a second. So magnitude is minus 2.5 times the log base 10 of the flux over the fiducial flux of an A star plus the magnitude of an A star. Okay, and this bit and this bit are just numbers that you look up, or I hand to you. So this is a magnitude. Magnitude is log base 10 of the flux. Normalizing stuff, doesn't matter. It's not. There's not physics in that. That's just units. So if I want B minus V, if I want the B band flux is going to be minus 2.5 times the log base 10 of the flux in the B band over the fiducial stuff, but this is the important part, the flux in the B band. This is the B band flux. That's how much light I get in this frequency range centered on a particular frequency with a width of a particular frequency. So that looks kind of like this. If I have my black body, everything comes off a black body because it's such a useful curve. Later on, we'll break it down and not use black bodies all the time. And most of the stuff that we do is generic, but we come back to a black body because it's a great source. So the B band flux is just going to be this part. Oh, no, sorry. Let's draw in the right spot. It's going to be this part over here. So what we want to do is just ask what is the value of my curve here. Does that make sense? I just want to know what the value of this function is at that wavelength. And I want to do that with an integral. The integral that I do, so we need to get at what FB is. So FB, I'm going to add up all of the light of, so this is my transmission function. We'll call this T. And it's a very narrow Gaussian that's centered on this wavelength here. And it says that we're going to use these wavelengths here, but none of these. So it's 0 over here, effectively. And basically 1 right here. So the transmission is a Gaussian, e to the minus lambda naught squared over 2 sigma squared, where sigma is the width of my Gaussian. So what I'm going to do is I'm going to take my black body, we'll just call that B for now, times my transmission function, and we're going to add them all up over all the wavelengths. So we're going to integrate over all wavelengths of the product of the black body times the transmission function. Is that confusing still to anybody? Or is everybody pretty sorted with that? Holler if you need me to explain that again. So this is a thing, it's kind of like a switch. So you think about the transmission function as a switch. It's just saying, I don't want this, I don't want this, I don't want this, I want this, I want this, I want this, I don't 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 want this. Except instead of using zeros and ones, we're using a binary function, or we're using a Gaussian function because it's smooth and continuous and integrates nicely. So this is the main thing that we're looking at. So the first thing that we need to do is sort out our filters. So we're going to do this twice. So we're going to do this for 2b, and then we're going to do this for the visual magnitude here, which is this one. The reason that I want to do this is because if I can get the slope of this curve right here, then I know what the peak of the black body is. Does that make sense? So if I know what the slope is, then I know where the peak is. And that's what I want, because I can't see the peak with my telescope because it's in the ultraviolet. I just need to see the slope because that's the telescope I've got. So, so we get a couple of things. So we need to know the wavelength for the visual filter. We need to know the wavelength for the blue filter. We need to know the width of the visual filter and the width of the blue filter. And we'll use these to make 2 Gaussians. We'll just call them G. We'll call them GV and GB because I don't feel like writing everything up. But this is a function of wavelength. It looks like that guy there. Times some normalization constant, which makes it add up to 1. That's necessary. So what we do is we find the B band flux is the integral of my B filter times my Gaussian, and then I integrate over wavelength. And my V flux is the integral of the Gaussian centered at the V frequency times the black body, d lambda. So that is what I just say through all of this business. And then I show you how to plot stuff. So there's a difference between the full width half maximum and sigma. Sigma is what goes into the Fourier into the Gaussian. But the full width half maximum is easier to see. So if I have a Gaussian that looks like this, sigma is where the value, if this is 1 here, sigma is where this is 1 over e. But the full width half maximum is where the vertical value is 1/2. So it's a little different, but they're related and you can compute it. But the full width half maximum is the thing that you can do by eye. I can say, well, that one has a width of that. But sigma is a little harder. So here we have a Gaussian, and I give you this Gaussian, and you can just use it, which gives you a Gaussian that's centered at the center with the width of this. So what this code does is it changes the width, the full width half maximum to sigma. I should have called this sigma, not width, but it's what it does. So you get sigma here, and here's our Gaussian, e to the minus L minus the center squared divided by 2 times the width squared. So this gives us a Gaussian, and then we normalize it. The norm is just the integral. So the integral is just dl, that's my wavelength size, times g1, and then we add that up. That's the norm, and then we divide by that. That way, when I integrate this thing, it adds up to 1. Oh, I should move my camera over here because that's what I'm for. So to compute the frequencies, lambda b is the frequency that centers. Why is that not highlighting? That's annoying. Lambda b is the frequency that centers the b frequency, and full width half maximum b is the width of the b frequency, similar for v. So we make TB, which is a transfer function, the transmission function, and that's just this Gaussian centered at lambda b with the width of full width half maximum. And then we compute the flux in B, which is just the transmission function TB, which we just computed here, times my black body S, which I plotted up a little bit, times dx, and then we add it all up. And that gives us the luminosity in B. That's this point here. The luminosity in B is going to be this point here. And when I plotted this, I used the second axis for the filters because they are not on the same scale, but that's a minor point. So then color is just B minus V. It's just minus 2.5 times the ratio of the logs, plus some constant that's based on vega and units that I gave you. So problem 1 is just plot a black body. And the black body is given above, and the temperature of the sun is given above, so all of this is given in bits earlier on, so you just do plt.plot. In the second one, I wanted you to compute LB and LV. So I wanted you to make the B and V filters. Oops, come back. And then compute LB and LV, and then plot them on the curve. And your solution should look like this, and some of them did and some of them did not. But that's all right, because again, I'm not grading for accuracy on these.
I was having trouble where both sections were fine on their own, but when you put the scatter on the Gaussian just went flat, and I don't know what was happening.
Probably you're off by a factor of C somewhere. So when you were doing this, when you had the transmission functions, if you plot the transmission functions and the Gaussians on the same axis, one of them is going to be flat.
Okay.
When you do the integral should not come out to be flat when you just have this scatter if you plot the right thing. I'll put up the solutions later today so that you can see how it actually ought to look. But typically, if you didn't get this, basically, so what you need to do to get this, where's my, that isn't my solution. Oh yeah, here it is. So to get this solution, you compute a Gaussian at TB with a width lambda b and with a center lambda b and a width form b. You compute the luminosity by doing this integral. And then you use scatter. The x-axis has to be the wavelength, lambda b, and the y-axis is the luminosity, lb. A lot of people flip those or use the luminosities, use the wavelengths here, or use the transmission function here. All of those will give you something that doesn't look like this. And then the last bit, compute B minus V for the sun. I get 0.52, which most of you also got, about 0.52. Or you had an error and your luminosities weren't quite right. Why is it 0.52 and not 0.6? So, okay, I get a value of 0.52 for the color of the sun. Is that more blue or less blue than the color that? More blue. More blue. Lower number is more blue.
So it's the Earth atmosphere?
Not the Earth's atmosphere.
Oh.
Let me try that again. Not the Earth's atmosphere.
Stellar atmosphere.
It's the sun's atmosphere. What is the sun's atmosphere doing?
Absorbing.
Absorbing what?
Photon.
What kind of photons? Blue ones. We got there. I hope that didn't. I hope that come out as funny and not snarky. Sometimes I can't tell if I'm coming off as snarky from up here. I never intend to be. So we're kicking out the blue photons. So what's going on? We have this is what we see. This is a dimmer in the blue than this one. So we're kicking out the blue photons by the stellar atmosphere, which segues into what we're talking about for the rest of the day. So how do we get this? How do we get this actual value? Well, we got to sort out what's going on in the sun's atmosphere. Does anybody have any questions on the numerical hallmark? Yeah.
Sorry, this is more about just the concept in general, but just to clarify, by looking at like the lines that we're reading from like the emission lines or the absorption lines, that can tell us what's in the sun?
Yeah, the lines tell you what's in the sun.
Okay.
The lines tell you what's in the atmosphere.
Right, sorry.
Yeah, no, it's an important distinction though, and a small distinction. And we'll go into that. So let's see. So I'm going to mostly talk today about stuff that was in the last reading. The stuff that was in the reading that was due today, which only like half of you did, is less important. So I don't really care if you didn't do this reading. You probably should go do it just so that the points show up. But I'm not as worried about the stuff in this reading. The reading that was due last week is very important. The reading that's due Wednesday, also very important. So 9.1 and 9.2 are super important. 9.3 and 9.4 are not as important. There's some pieces that that I care about, that I'll ask you about, or that I'll talk about. 9.5 is important again, so make sure you read that one kind of carefully. But it's a short section. There's not a lot on there. Okay, chalk. Oh man, this is only a tiny chalk. I need a real chalk. So today we're talking about radiative transfer, and I'm going to go back. The book doesn't do this nearly as doesn't do this in as big of letters as I think he should. Sorry, I need to make sure that this is really a kappa nu. So this equation is part of the radiative transfer equation. The other part of the radiative transfer equation is the source, which we'll talk about in a little bit. Maybe I'm not going to get to sources today. Maybe I'm only going to get to things being in the way. If I put that down, can you see a little better? Is that better? There you go. That's better. Fortunately, okay. So what does this say? So what does this first part mean? So what is I? Somebody yell something out.
Intensity.
Intensity. What is it telling me about?
Star bright.
Star bright.
The intensity of light on an area.
Right. Physics units. Okay. So it's in ergs per second. So it's the number of photons per unit stuff. It's the specific number of photons. So it's in ergs per second per wavelength per area per solid angle. And there's a cosine theta in there.
So what's the difference between steradium and solid angle?
That's the same thing. A solid angle, just like it's like the difference between angle and degrees.
Okay.
The angle is the thing, and the degree is the unit. Steradian is the unit. That's a good question, Nate. So what does this say? So this is photons. S is path length. Okay, so what does this first term tell me about, what is it telling me? This is a mathematical sentence.
Angle, oh, change in path length, or no, change in intensity per path length.
Yeah, so it's the change in the intensity as you move along the path length. So if I have some cloud of stuff, let's make it good and fluffy. Clouds are all real fluffy. Even clouds in outer space are all real fluffy. I have my path goes like this, so this is S. My intensity is on that, and that falls down. Why does it fall down? Because I have crap in the way. So this isn't like a single thing, this is a packet of 10 to the 70 photons. And some of them, some fraction, F, get kicked out by various processes that we will talk about in horrible detail. But right now, for this moment, we only need to know that some of the photons don't make it through the cloud. So here I am over here catching my photons, some of my photons lose. That's what this says. This is the change in photons with respect to path length. Well, the right-hand side says, this, we're just gonna call this F times I. And it's negative. So okay, what is it being negative tell you? I is a positive definite quantity, okay? I can't have a negative energy in photons. I can have negative energy, no problem with negative energy, but negative energy in photons, that doesn't make any sense. I is positive definite. F is a fraction, that's just gonna be a number that is gonna be positive. So this is a negative quantity. Being a negative quantity, what does that mean for the light as it goes through the cloud? It decreases, it goes down, right? How much does it go down? It goes down by some fraction proportional to itself. So some fraction of itself. So we have this, I'm going to write this up again. di ds equals minus, well, we'll just call it, minus a times I. As long as a is not a function of s, if a is a function of s, then you don't have this equation, right? Then this is an exponential. I equals I naught, this is the radiation at the source, e to the minus a times s. You just memorize that equation. I don't tell you to memorize very many equations, but don't memorize the equation, memorize the differential equation. Forget about the I, you can swap out I for f or whatever else, all kinds of functions.
So, in differential equations, we get I naught from initial conditions. What will be the initial conditions in this case?
The initial condition is I start with some radiation field here, I naught.
And
The path length would be 0.
And at a path length of 0, I have I naught. So that is computational problem 1, is what is the radiation intensity at the source. Computational problem 2 is what's the crap in the way. So problem 1 is what's the source function. And if we're in a nice ideal world and this is a black body, what is this? And there's no atmosphere. Let's say there's nothing in the way and there's not an atmosphere. What is the intensity, the bolometric intensity for a black body?
it's
Who's a?
4.4.
There you go. I know this, I can get this a lot of the time, right? But sometimes I can't, but that's the thing that I want to figure out, because I need to figure out what the temperature of my star is. And then the other thing is this. So, okay, AS, let's talk about that for a second. What is that? What's it doing? So, let's talk about path length for a second. Let's talk about random walks for a second. Where'd my eraser go? There it is. Yeah.
Does luminosity come into the equation? I mean, does area come into the equation? Isn't that for luminosity?
Yes. So, yes, if I'm looking at a total source, that I would put the luminosity in here as my initial source. That would be what that is. It's all of the photons coming off the star. So the area would factor in for this as well. This isn't that quite that specific. So depending on what you're doing, change it on what I naught is. But if what I've got is a measurement and I want to measure the source, then in there needs to be an area. It's not immediate where it ought to go. This will make more sense later. For now, area times sigma t to the fourth is going to give me my luminosity, whatever my brightness is at the center, right? And then the decay will tell me what's in the way. So let's talk about the decay for a second. So we've talked a lot about what the source ought to be, and usually it's a black body. So now we need to talk about how things fail. So how do you get rid of stuff? So we talked a little bit about mean free path.
Means that it comes from luminosity.
Was that?
I think you mean like it comes from the luminosity, right?
This.
It's an intensity, but
Yeah.
I mean we can factor in area on both sides of the equation, right?
Yes.
Factor it out. So luminosity, the same equation will work for luminosity
Yeah.
of the star as you go away. Okay.
I can do this for several different things. This can be the flux. This can be the radiation pressure. This can be the mean intensity. This can be all kinds of a lot of different kinds of things have a functional form like this.
So intensity is like the power of the light source, and the luminosity is like the total output using that power?
The total luminosity, so yeah, so trying to decide how deep down this rabbit hole I'm
Sorry,
gonna
this is
go.
very tangential.
No worries. Well, I want to give you a satisfying answer, but I don't actually have a satisfying answer because the real answer is I can plug in some stuff here and I can plug in some stuff here. Depending on if I'm looking at a resolved object or an unresolved object, I need to interpret this as the flux or the specific flux. So kind of depending on the scenario, this will change a little bit what it actually is if I'm looking at the bolometric flux or the spectrum. The important part is the source and the decay. So let us talk about the decay for a second. Let's not worry too much about what the source is. So we talked about mean free path, and we said that lambda, the mean free path, is 1 over the density times the cross-sectional area for that object to run into something else. And the cross-sectional area is really complicated. It's a really complicated function of frequency and a really complicated function of the state of the object, because neutral hydrogen, if I'm a radiophoton, has no cross-section. Ionized hydrogen, if I'm any kind of photon, has an enormous cross-section because I've got all these free electrons, and free electrons are huge if you're a photon. The scattering cross-section is large. So sigma depends on a lot of stuff. But another way I can write this is as 1 over kappa times rho. So the only difference is here n is my number density, and rho is my mass density. So the only difference between kappa and sigma is the mass of the particle. But so kappa is like the cross section of the particle. It's like how big the particle is. But that's a very complicated function. So what we need to do is, so if I need to say what is my total, what is the total flux that I observe, it's going to be the flux at the source. So this is a function of wavelength times e to the, so let's do this a slightly different way. So my radiative transfer equation goes di ds, this is how much I lose, this is how much light I lose along the way, is minus kappa, this is my my cross-sectional area, times rho, this is the mass density of the stuff, times I can integrate this, and this becomes I equals I naught times e to the minus tau, where tau is kappa times s times L, the total path length, times d times rho, the mass density. and this is called the optical depth.
So what is tau again? What does that say?
Tau equals kappa times L, the total length of the cloud, times rho. Yeah.
And that's equal to AS?
That would be AS over here. Yeah. So the optical depth, so what this says, so this is the light that comes off the source, and this is how much it gets attenuated by the stuff in the way. So the optical depth is what? That's going to be how much I've dropped. So if I have an optical depth of 1, how much of my original source, roughly, do I have?
1 over E.
Yeah, about half, right? E is about 2, so you get about a half. So when you're down 1 optical depth, you've lost about half the light, but it turns out that's a significant fraction. Okay.
So
Yeah. Yeah.
oh, this is also a bit tangential, but does this behave just like a half-life function?
Yeah.
Okay.
Exactly, it's exactly the same. It's just exponential decay. You have, and that's a great question. I love that question because it's in fact identical physics. Because I have some quantity of stuff. I have some rate at which a fraction of them is going to decay. So it's just I have some fraction in a certain time period that's going to decay, and that gives me that. That gives me this. So for like nuclear decay, I have a similar expression. Okay, so let's talk about the various sources of optical depth, of opacity. Actually, oh no, I already turned the thing off. I pulled up this great, as I was writing the homework, I pulled up this great image of the solar black body. So this is what a 5777 black body looks like. Maybe you have to use your imagination to put things in the right shape. So pretend that this is 5770 Kelvin black body. The solar black body, let me get a different color. I know that yellow. There it is.
Human yellow.
The solar spectrum actually looks like this. There's some lines up here too. So if I look at the opacity is going to look like this. That's not to scale or even remotely accurate. This is a cartoon. I've got all of these spiky lines because what is this one? This one is, say, this is the 2-to-1 state of of neutral helium. Which, if I'm a photon, only exists when I'm at this wavelength. Like this line, if I'm a photon, only like this material only shows up if I'm a photon of this frequency. So there's all kinds of complicated things. This is why we get the Roslin mean opacity, which I'll explain and define in a second, but the Roslin mean opacity is a way to take this nasty-ass curve, divide out everything that is generic so that you have just a number that applies to a material. So I have, say, helium, I can get what the Roslin mean opacity is, and then I can do some math with that. So that I can get what the optical depth actually should be for my atmosphere. So let's talk about the various places. And people who have a lot more ability to focus on small details have tabulated huge tables of stuff that, that's way outside of my skill set. But there's 5 main sources of opacity. bound free. So in all of these, I start off with a photon and a thing, and I end up with the thing in a different state. Or sometimes the thing and the photon again, but only some of the times. In most of these, the photon is absorbed. You never get a half a photon, so you don't have a scenario, say I've got 10.2 electron volts for that ground state hydrogen transition. If I've got a 20 electron volt photon, it's not going to give off only 10 volts to the atom and then keep on going. It gets absorbed completely. And then that atom has the remainder is in the kinetic energy of the atom. So we have bound free transitions. I got a neutral hydrogen atom. What do I have after this kind of interaction? What do you think? Think about the electrons. This is called bound free. So I start off with a neutral hydrogen, and I'm left with a free electron. So I also have ionized hydrogen. That makes sense? So here I've got something that's neutral, and I kick off an electron, or something that's slightly ionized. So this is kicking off an electron. So this is also called photoionization. I should have started with bound. That would have made more sense. But we already started here. This is what the book does. So this is photoionization. And let's see, the cross-section for photoionization is actually, for hydrogen, is actually relatively simple. 1.3 times 10 to the minus 19, 1 over n to the fifth, where n is the state of the electron, lambda over 500 nanometers cubed. And this is in meters squared. This is a relatively straightforward.
What is the power of n?
So this is the level.
What's in the exponent of n?
5. So that's a relatively simple cross section. A lot of these have much worse cross sections that I'm not going to be able to write down. So this is kicking off the photon. So we can also talk about bound.
So we're talking about collisions here?
We're talking about a photon hitting a thing.
Okay.
So we have a photon plus thing.
Right, so then this is the cross section from the collision.
Yeah, so this is the photon impinging on, so photon plus thing goes to other thing.
Mm-hmm.
Maybe plus a photon. So there might be a photon at the end, there might not be. So with bound free, the first thing is a bound hydrogen atom, and the other thing is an ionized hydrogen atom, or helium, or calcium, or whiskey. They're whiskey molecules. Bound, what do you think that is? So if I start off with a ground state hydrogen atom, I get a higher state. So thing is a bound hydrogen atom. Other thing is an excited atom. These cross sections are silly complicated. So this is photoexcitation.
So both things are ionized in the bound and
No,
No.
nothing's ionized here.
nothing is ionized here.
Or maybe ionized once, but you don't change the ionization state. So
no-
I can have bound for say helium-2. So helium-2 is a helium with one electron removed. So I can have helium-2 goes to helium-2 star, which is excited. So those would be my two bound states, even though I'm starting with something ionized. So it's about whether or not you lose an electron in the process.
So if you don't lose an electron, it's bound.
It's bound.
But you do lose an electron in bound free.
Bound free kicks an electron off. You never lose it, it just comes off the atom. There's free bound too, but what would that give you? So if I have if I'm talking about free bound as a process,
Would that cause
would
it?
Kick off the photon.
It would
That-
emit,
yeah, that's gonna emit a photon equal to the binding energy. So free bound would be I have a free electron and a bound and an atom that can accept an electron, and then in the end I have a bound state. I don't need an electron, I don't need a photon for that, that's just gonna naturally happen, and that produces photons. So that's not a source of opacity. But it's another process that also gets talked about, because it's another source of light. But it's not a source of opacity. And then the last one is free. Now, in this process, the photon is absorbed. This is different from Thomson scattering. So this is also called Bremsstrahlung. And do you speak German? No, but a little bit. All right.
2 years doesn't count.
2 years of Italian.
2 years of German doesn't count.
Yeah. Okay. So
He speaks every European language.
that's a lot of languages. I mean, at least two. So Brems means breaks, and Strahlung means radiation. So this is breaking radiation. So what happens in this process, I have a free electron, and I have an ion. Turns out the ion is important. The photon hits the electron, gets absorbed, and the electron scatters off this way. It's got to be done in the presence of an ion, because otherwise you can't conserve momentum and energy. There's quantum mechanics involved, and I'm not going to go too deep down that road, down that
Is that
hole.
is that an E after the R in Bremsstrahlung?
BREMSTRAHLUNG.
What?
It makes sense if you speak German already. German is a great language because it totally makes sense once you see it. Like they have these huge words, but they're just sentences
Stack
with the
words
spaces
together.
Yeah,
taken
they're
out.
the
Makes sense.
ultimate compound
Yeah,
words.
you'll always hear,
Yeah.
oh, German has a word for that. It's like, no, they did 2 words and slam it
I know,
and called
right?
it a word. They don't have a word
The
for
longest
that.
word in the German language is the one that you came up with. Right? Okay, so that's free. So okay. So if I have an electron and a photon and they smash into each other, one of 3 things can happen. I think only 3. I didn't do my research for this. This is a little extemporaneous, but okay. So the first thing that can happen is the photon is absorbed, and the electron is accelerated, and then the electron is decelerated. By the ion, which kicks off another photon. That's a lower energy photon. So this is free. That's complicated. Thomson scattering. Thomson scattering is inelastic scattering. No, sorry, elastic scattering. So Thomson scattering is perfectly elastic scattering. Everybody has the same energy that they came out with. And then the third thing is Compton scattering. And here you have a free electron and a photon. They scatter off each other at some angle, and the energy of the photon changes. So, these are 3 processes that we've talked about a couple of times. Oh, I should put the camera on a little bit of the order. So those are 3 processes that we've talked about several times. I would encourage you to make a note on that and make sure that you separate these 3 processes. Yeah.
Did you say when it's decelerated in the first one,
also spits out the photon.
Yes. Because so the electron is accelerated by the photon, it hooks around the ion, and as it hooks around the ion, because I have an accelerating charge, I get another photon. Every time you accelerate a charge, you get a photon. And you lose some of the energy from the thing.
So for free you have a reaction, but for the Thomson and Compton you don't.
You have a what?
Reaction.
There's always a reaction. I mean, there's always something that happens. So I'm not sure what you mean by reaction.
Like, I guess something gets taken out of the electron. Like a change happens in the things that are colliding.
They always change. All three things change. All of the things change, but only one of them do I actually lose a photon. So.
I don't know.
Okay. So all of these look like photon, electron, photon with some other energy, electron with some other energy, except for that one where I don't get this other photon, because it just gets absorbed. Does that make sense?
I think so.
Okay. So completely inelastic,
Okay.
completely elastic, sort of inelastic.
Okay.
In Compton scattering, we don't lose the photon.
Right, because when you're talking about an elastic, the like completely elastic, that doesn't change the things that are being hit, or does it?
It does. Elastic scattering does not change the energy in the system.
Okay.
Compton scattering changes the energy of the photon
Right, because it's not
and changes its energy.
fully elastic.
But Thomson scattering doesn't change the energy of anybody.
Okay.
Okay, so then we have Thomson scattering. Then we have, so the first three are atom processes. So there's got to be an ion nearby. The fourth process is Thomson scattering, or electron scattering. Oh, time to go.
Oh.
And the last one is the H minus ion. And we scatter off of that. So it's Thomson scattering is scattering off of free electrons. H minus is scattering off of H minus atoms. So the H minus is a really big atom as far as the electric field is concerned, because it's got an extra electron. So it's got the cross section that looks kind of like an electron but bigger. So how do I make that? Well, I mean, if I've got my hydrogen atom looks like this. Here's my proton. Here's my electron, which is in kind of a cloud over here. Since my electron's over here, I got this other electron that comes in and sees, hey, this guy looks kind of positive. So he kind of loosely hangs around. So you get this real slightly bound electron onto my already neutral hydrogen atom because of the because of the polarization. So this electron shows up. The other electron goes over here. He thinks he can join. He can't really because he's not really well bound. But this is a thing that happens in cooler stars. So it's got to be pretty cool because the binding energy of this is only like half an electron. I think that's all I have to say for the day. I forgot I didn't get to temperatures, and I didn't get to LTE, but that's okay.
Sorry, we got into the warrants on this one, didn't we?
No, that's about where I got.